In this recording, we'll work a few examples, a few conceptual question examples, and one question that will work in the numbers. Okay, now in this first question, we are asked to compare the electrical potential at point A to point B, knowing that we are in a region where we have a uniform electrical field pointing from A towards B. What you need to remember is what we just learned is the fact that the electrical field is going to point downhill in terms of electrical potential, meaning the electrical potential is going to decrease in the direction of the electrical field. So that tells us right away that the electrical potential at A is larger or greater than the electrical potential at point B. One interesting thing to think of here, the force acting on a charge due to the uniform electrical field is F is QE. Now, if I'm going to move a charge Q from point A to point B, now I'm going to exert that force F, and I'm going to move it a distance, let's call it D. So the work done to move the charge is going to be equal QE times D. Now this is the work done to move the charge. I was not very careful here deciding on the directions, but let's do it right now. If my charge is positive, then the force, the electrical force, is going to point in the same direction as the electrical field. And the force that I need to apply while it is moved there from A to B without accelerating is going to be in the opposite direction. So this is the force exerted by me or you. This is the applied force. Now, which means my work is going to be negative, the work done by me. Which means that the change in electrical potential energy is going to be negative, minus Q E times D. Okay. Now, if the charge was negative, then negative times the negative, we are going to actually, let's think of it totally from the beginning. The electrical force would be the opposite direction, my force would be in that direction, so the work is going to be QED in this direction, so I'm not going to have this negative sign and so on. Okay, now the point here is this is my change in electrical potential energy. What about the change in potential? The change in potential is going to be the change in electrical potential energy divided by the charge. So it's going to be minus ED. Since here I had I moved in the same direction as E, I have a decrease in the electrical potential. If instead I move the charge from B to A, I would be moving towards increased electrical potential, and it would be plus ED. Okay, but this is one expression that we are going to need to use later on. So let me write it down here. Delta V is minus ED, or ED, depending on the way we are going to move the charge. Let's look at this other question. Now here it's the same situation, but we have a conductor here. Point A and point B are within a conductor. The key here is to try to remind us of what happens in a conductor. Remember, the electrical field inside the conductor is zero. Throughout the conductor, the electrical field, when it is in static equilibrium, when it is in equilibrium, the electrical field is zero. If the electrical field is zero, it means I'm going to have the same electrical potential throughout that conductor. This is a key point that we are going to need to use quite a bit. Having an electrical field equal to zero, the equation that we just came up with a minute ago, ED is equal to delta V. Now if this is zero, that means this is zero. There is no change in voltage. That means the voltage throughout here is the same. The electrical potential throughout the conductor is the same. That's a key important point. Equal to. And that's because the electrical field inside the conductor is zero. Now, what about this case here? We have a positive charge. We don't have a uniform electrical field anymore. And it is asking us again to compare the electrical field at point A to point B. Location A to location B, not the electrical field, the electrical potential at location A compared to location B. Same thing as we did before. Consider the fact that from here to here, it's along a sphere centered by that positive charge, so we are along an equipotential line. So from here to here we don't have any change in electrical potential, but from C to B we are going downhill, so our electrical potential is decreasing, meaning then at C we have the same electrical potential as A, and at C I have a higher electrical potential than B, so the answer is greater than. Excuse me. Now, in this question here, it is asking us about the electrical potential at distance d, which is 0.53 10 to the minus 10 from a proton. Again, the electrical potential at infinity is 0. To find the electrical potential, we just use the expression. So it's 9 10 to the 9 Newton meter squared per Coulomb squared. That's my K. Times Q. Q would be the charge of a proton, which is 1.6 10 to the minus 19 coulombs, over R, which is 0.53 10 to the minus 10 meters. See, one of the meters cancels with this, one of the coulombs cancels with this. Okay, now here we have, I'll calculate it on the side here. So we have 9 10 to the 9 times 1.6 10 to the minus 19 divided by 0.53 10 to the minus 10. So that gives us quite a large electrical potential, 27 volts. Now, what is the electrical potential energy of an electron at a distance this much from a proton? This is essentially the electrical potential energy within a hydrogen atom. So all what we have to do is we multiply that voltage by the charge of the electron. So 27 volts times the charge of the electron, which is minus 1.6 10 to the minus 19 coulombs. So that's going to be 4.3 10 to the minus 18 joules. Okay, it does not look like a very large value, and it should not be. It's just one hydrogen atom.